Yes, and in particular about the three central stars, and I will do my very best to add more to the confusion. Of course, I don't have to give a big introduction. You know the region now well. It was introduced by the previous speakers. But I will give you an outlook through which I would lead you here. I will talk about the mass and the distance, how we derived it for S2, and what kind of data we actually used. And also I will then introduce a new practical method, how to derive GR parameters from orbits. And I will then use simulated stars, and we will derive a possible parameterization of getting the GR effects. And then in the end, I will try to apply this to S2. And all of this is mainly Mazia Paza's work, who unfortunately didn't come. But there is sprinkles of other contributions in here as well. So the data that we're using is the VLT data. It's our own observations plus archival data. So it's basically the same data that Stefan talked about, and also published KEK data, radial velocities, and so on. Then we went through the usual spiel of combining data and reducing data. So we flat fielded, sky subject, bad pixel corrected, and so on. And then we also combined the 13 milliarc second and 27 milliarc second pixel data that we have. And we restricted ourselves actually, just to be sure what we are doing, in particular for the registration, to data, to images where Sergei star was flaring as well. So we always would see Sergei star and the other stars. And then, as we said, as I said, we constrained ourselves to the three central stars, S2, S38, and S55 or S0102. Then the registration itself is, well, of the order of a milliarc second or 1.5 milliarc seconds for a single position. So we used the mesostar coordinates as well, as far as they were available to us. And as I said, we constrained ourselves to data that has only Sergei star flaring. Then the overall data linkage coordinate problematic that was also addressed. We, of course, were aware of that as well and looked into it. So we basically combined the VLT and the KEK data by simple scaling and shifting, and checked against rotation by using the overlap in S38 data, because that has a larger distance from Sergei star, shows probably less GR effects. So we can use that to clinch on and to avoid to a certain but very precise level that the two data sets are rotated against each other. So that all seems to work rather well. Then the models we applied, we used the Einstein-Infeld-Hoffmann equation to model the motion of the stars. And that collapses, that includes the motion, the drift motion of Sergei star, both in r and in velocity. And it collapses if you say Sergei star is compact, and then it boils down to the formula that we used already in Rubilar and Eckert in 2001. So this is how it looks like. These are the orbits of the three stars. Here we plot only the data that we input into the system ourselves. But as I said, on the right-hand side, you can see that we used KEK positions that were published by Böhle et al. And also radial velocities by Gillison and Böhle. So we used everything that we could actually combine. Then we did MCMC models, fits, both relativistically and non-relativistically, and came up with estimates of the mass and radius. And those numbers that we get here are consistent with what everybody else gets as well. So we're not too bad. The S2 periups question we addressed as well. We find middle of the year, and that's how it goes. So the relativistic orbits of stars and general relativistic effects. So there's a few phenomena that have to be taken into account. There's basically the low order effects like redshift, and that were addressed earlier, and then also effects on the long axis and on the ellipticity of the orbit that will change during the orbital phase. Yeah, well, but you also have a larger error. So I think the orbital elements are sufficiently unsecure to make a very, very firm statement. But that depends on the amount of accuracy that you think your data has. So I think we are in agreement, but you may be right with your fine statement. That's okay. Higher order effects we did not look into, like frame dragging or gravitational lensing. And one has to point out there's three major contributions to the periapse rotation. There's the periapse rotation within the plane, that's prograde or retrograde, depending whether it's relativistic or Newtonian. And there's also the problem of the dark mass that is surrounding such a star, possibly. There can be up to 10 to the 4 solar masses, 10 to the 4 solar masses in the form of whatever, black holes or something like that. And that can have some graininess. And that means the stars move in and out of the orbit. That means the potential on that level changes. And that can move your orbital plane back and forth a little bit. So that needs to be taken into account. We didn't do that in the FITs. I will say something at the end concerning that problem. So this is now the overview of the stars that were available. Basically, what we didn't use are the S stars here, the red ones on top. We just used the yellow ones, the three innermost. And these are the simulated stars. Here plotted in 1 minus e and periapse distance against the long axis. And what you see is that we try to get simulated stars well within the radii of the three closest stars. But we had to stop, of course, at the innermost radius at about 0.1 milliarcseconds. That is where stars would not survive and would be disrupted. So we covered basically the whole phase space with simulated stars. And those are plotted here again. The long axis and the eccentricity against a relativistic parameter that we choose. And in both plots, E and A are parameters here as well. The relativistic parameter was introduced by Zucker et al. And that is the ratio between the Schwarzschild radius and the periapse distance. Now, there's many relativistic parameters that you can think of, but that one in particular has the advantage that it is linked to things that can easily be measured, more or less, or inferred, and that is proportional to delta omega, that is the periapse rotation. Now, the method. Stefan pointed out that, in fact, you can fit any ellipse to the data and camouflage the relativistic effects. There's always a best ellipse that you can fit. So that is not the way to go. You have to be more inventive here. So on the left-hand side, you have the non-relativistic case. It's easy, few orbital elements, negligible computing time, it's quick. On the right-hand side, you have where the problems are born. It's a relativistic orbit. You need to have a central mass. Depending on whether you do it in a plane or inclined, you need to have 5 to 7 launching points for your star. You need to use the post-Newtonian formalism, which is an approximation, and you use to get something, a Runge-Kutta method or something like that to get your orbits, and that is rather temperamental. So you have to make sure that in the non-relativistic case, your orbits are always closed, and then you can switch on relativity and look at the result. So that makes a lot of headache, and that has also involves non-negligible computing time. So, but in any effect, the relativistic orbits can now easily be parameterized, and we need to find a simpler method to describe the relativistic character of an orbit, and preferable by simple non-relativistic orbit fitting, because that's quick, combined with suitable parameterization. To do that, we introduced the method of squeeze states. That is, you have the product of two quantities which are limited by a small number, epsilon here, and if you choose alpha and beta as your fitting or your goodness parameters, like e to the minus chi square, then you can write it like this in the second line. And what we do here is actually we take into account the modification of the orbital shape due to relativity. That is, we fit the lower and the upper part of the orbit separately. And the lower and the upper part then also can be subdivided into a systematic misfit due to the fact that the lower and upper part now don't belong to an ellipse, but to a Rosetta-shaped orbit, and to a random part, of course, that's due to noise. Alpha and beta are just two quantities. Yeah, think of it. Think of it as the uncertainty principle, right? This is delta x and delta p. So if you get one exact, the error moves to the other, right? You will see now in this graph. This explains what we mean. So here we have the dashed line is a Rosetta-shaped orbit, and the two colored lines, the red one and the blue one, are fits to the upper part and the lower part of the orbit. So if you fit the upper part nicely, yeah, the lower part is messed up and vice versa. So you basically squeeze the uncertainties of the orbital fitting to one side by fitting the other much better. So doing that, then you can define yourself a ratio that is, for instance, the fit of the general fit of the upper side divided by the better fit of the upper side if the lower side, or by the worst fit of the upper side if the fit to the lower side is optimum. So in how far your fitting quantity deteriorates by just constraining yourself to one side is a fit, is a measure of relativity, is a measure of the misfit between the ellipse and the Rosetta-shaped section. And that actually can be parameterized with a relativistic parameter. So you see the ratio is 1 if it doesn't matter, if you have an ellipse, yeah, and the relativity effects are very, very small. And the ratio becomes much smaller if you go to a higher relativistic case. So that misfit parameter could be used, but actually we are using other quantities which behave similarly well. That is the change in the long axis of the different fits and the change in the ellipticities of the different fits to the lower and the upper orbit. And also you can also use delta omega, which is basically the same, but with respect not to the upper and lower orbit, but to the left and right side, to the ascending and descending part of the orbit. So that's depicted here. So you have a delta E and delta A if you compare the lower and the upper part of the orbit, and you have a delta omega if you compare the ascending and descending part of the orbit. So all of these 4 quantities can be used to measure the misfit, i.e. the difference between ellipticity and a Rosetta-shaped source. So that has now been done with our simulated stars. Yeah, there we had the orbits at hand and could determine all these quantities. And here again you see the ratio of the A ratio, the lower fit to upper fit A ratio, A value ratio, and you see if it's non-relativistic, if you're close to an ellipse, that ratio is 1, and it decreases if you go to the relativistic domain. Similarly here, the ratio in ellipticities is 1, and then decreases if you go to relativistic orbits. So this is a very nice way to characterize the relativistic character of your trajectory. And here the same result for delta omega, which is proportional to the relativistic parameter that we introduced. Again, delta omega is 0 here in that case. If you're non-relativistic and becomes larger, the more you are relativistic. Now, question. Of course, we want to use this. Is the current single-dish AO dataset for S2 accurate enough to show the effect of GR? The procedure is clear. You take the S2 orbital data, determine the A ratio and the E ratio and delta omega, and compare it to those graphs that we derived. So that's the result. So you have to squeeze yourself up into the corner where you're hardly relativistic. And you see that if you take the mean with the conservatively dialed through uncertainties through the whole system, then it looks rather insignificant. It looks more significant if you take the median. But as I said, this is for delta omega the same case, so you do see an effect. But as I said, the uncertainties have been dialed through the entire process, reference frame, uncertainty in positional fitting, and so on and so forth. But for S2, since we have used only data that contain Sagittarius A star flaring, we can restrict ourselves to the positional uncertainties in that case as well. And then we can, as we pointed out in the paper, we can, in the section 5.3, we can make a Gedanken experiment and assume that about 5 or 9 measurements fall on each orbital quarter and result in a displacement of that quarter. And then you can think about the possible combinations that you can have and find then by just thinking about it that there's a 3 to 4 sigma significance in that involved if you get all quantities, the A and the E ratios and the delta omega on the right side of the distribution. That has been quantified here now. So we take 7 data points, we use 1.5 milliarc seconds as an intrinsic uncertainty of the positional measurements, and then we are allowed to shift to the left, right, up and down, or just leave it each orbital quarter by about 0.5 milliarc seconds. and we can look at the distribution, and then we can determine these quantities. As you can see here, it has an effect, how you shift it has an effect on the ellipticity ratios and on the A ratios, or on the delta omega, depending on what you do. And these are distributions. For E and A, they're not that nicely Gaussian, but for omega, they're very nicely Gaussian. The 1 sigma point is indicated, and the measure of S2 is indicated as well. So if you judge on the significance of the measurement that we did with respect to a noise-dominated model, you find that the values we extracted are all outliers and indicate that there is a 3 to 4 sigma measurement here, or a certainty here. So that is a visualization of the effect. And as you can see, while the periastron shift is actually taking place while S2 is swinging around Sag star, the effect of it with single dish telescopes can more easily be measured if you look at the entire orbit, because the long axis gives you a lever that increases the effect on the angle of the angle has, the angle delta omega has. So there's a difference in the orbital position that can actually be pinpointed the way I explained. So that led to a nice ESO-Press announcement, which everybody was able to look at. Now let's go to the graininess that needs to be mentioned. It needs to be taken care of, and it so happens that the number of bona fide black holes, as you could determine them in the X-ray domain, as X-ray sources, increases towards the center. And so there's quite a number of them. And in any way, the assumption is that a large number of remnants will sink to the bottom of the potential well. And if you assume 10 solar mass population of black holes that you wouldn't see, that could contribute to the dark matter, you would have that graininess effect. It becomes more and more grainy the more mass you allow for your black holes to contain. And as we have shown in the paper Sapra in 2012, that effect can be substantial. So here we have taken 2,000 solar masses in 10 or 20 solar mass black holes, and it can actually contribute to the periapse motion. So what is shown here is that for different cases, the periapse motion shift, and the GR effect has been taken out, the 11 minutes. And you can see that it can contribute significantly and even can go the other way, depending on what the distribution of masses is. So the graininess needs to be taken into account. However, if you look at the amounts, a few arc minutes, and the exactness, although I think significant, of our measurement, we can't make any statement about this, and higher significance is actually needed, or more precise measurements of the effects are needed to make a statement on the graininess of the dark matter around Sag star. So as a result, we got a mass and a radius, a distance, which is in agreement with most other derivations. We have a periapse time, which has a large uncertainty, but which is also fine. So it tells you at least that it's going to be somewhere it's actually not July, I see here. Yeah, whatever. It's going to be in mid of next year. And we do have a measure of delta omega, and I think it has a 3 to 4 sigma exactness on it. So the uncertainty is probably rather 3 minutes than 7 minutes, as we got from just dialing the uncertainties through the system. And the expected value is 11, and we measure 14. And we can also determine the relativistic parameter. We would expect 0.00065. We measure 0.00088. And the uncertainty here is probably rather 0.0004, depending on how you actually do it. And summary. So we got mass and distance both with Newtonian and post-Newtonian solutions. We developed a new method to determine the degree of relativity from orbits. And we got a measure that is probably a 3 to 4 sigma event that indicates that the quantities, the relativity quantities, are of the order of what you would expect them to be. So if that is true, and if you accept that, then S2 would be the first star for which that could be done. And it can only get better, so we are all looking forward to more precise KEK and VLT data, and also to more and new VLT gravity results that probably Frank will allude to. Thank you very much.